Hi, everyone. Welcome to our first lecture video. I'm testing out this system where I am recording this using Zoom so that you can have my face in the corner here while the slides are up. To sort of hopefully mimic the classroom lecture feel a little bit so you can hear me talking while the slides transition, things like that. If this doesn't work, or if anyone has any suggestions for what they think would work better, I am all ears. Feel free, please let me know, and we can sort of try to work this out together. So, uh, first video is going to be pretty short. I'm just going to try to explain what thought experiments are, what role they play in philosophy, and why we use them. So, first things first, what is a thought experiment? Well, a thought experiment basically is just this hypothetical case. So it doesn't have to have ever actually happened. It doesn't have to ever actually happen. It might not even, strictly speaking, be possible to happen in some sense of the word possible, which we'll talk about a little bit uh, later in this video. But a classic example of a thought experiment is Schrodinger's cat. Most people, I think, are familiar with Schrodinger's cat, or at least vaguely aware of it, have heard of it maybe. And Schrodinger's cat is a thought experiment. If you're not familiar, Schrodinger's cat is a thought experiment from physics by a physicist named Schrodinger. And Schrodinger's cat is a scenario where basically he says, let's put a cat in a box and a little sort of spin measurement system that will measure the spin of a particle. And if it spins right, the poison comes out and the cat dies. If it spins left, then it doesn't, or something to that effect. And according to the Copenhagen interpretation of quantum mechanics, until we measure and open the box to see what happened, the particle should be both spin left and spin right, which means the poison both should and shouldn't be released. So the cat should be both alive and dead. And that's a thought experiment. No one's ever actually put a cat in a box with some poison and a measurement system. I don't know if we just logistically could, even if we tried. It would probably be morally wrong to kill and or not kill a cat just to try the experiment in real life. So it's just a thought experiment. But it's still supposed to tell us something important about physics. Schrodinger thought that it told us that the Copenhagen interpretation of physics was wrong. And we'll talk about that a little bit later. So, thought experiments are cases like Schrodinger's cat. They are imagined hypothetical scenarios. So they don't have to be real. They don't have to have ever happened. They don't have to ever happen. But they just have to be sort of coherent. We have to be able to talk about them. They have to make sense enough for the thought experiment to make the point it's trying to make or to raise the issue that we want it to raise. So most thought experiments, like Schrodinger's cat, and like some thought experiments we'll talk about later in the course, like the utility monster or the experience machine, or Mary's room, where Mary is a scientist locked in a room that's all black and white. That's a thought experiment about the philosophy of mind that we'll talk about later. And most thought experiments are designed to test some theory. They usually take extreme cases, so way sort of out there, which is why they don't have to really be tied that closely to reality. They don't have to actually happen or be, something we could actually pull off in real life. They're designed sort of at the borders of the theory, at the edges of what could possibly happen. They're extreme cases to illustrate the limits of a theory, to see, is a theory right? Is it wrong? Does it get it right in sort of these out there far away cases? Because it's pretty easy to come up with a theory that gets sort of the basic normal cases right. Newtonian mechanics, for example, if you've taken a physics class, is a theory of physics that gets it right at sort of the normal level stuff. It gets it right for how cars work and when a bowling ball falls and the friction of tires screeching to a halt. That's all well described by Newtonian physics. But it's at the extreme ends, the really, really tiny small stuff like the electrons and quarks, tiny particles. Newtonian physics gets it wrong. At the really extreme big stuff, black holes and supernovas, Newtonian physics gets it wrong. We need relativity. We need quantum physics or quantum field theory for the tiny stuff, and general and special relativity for the big stuff, like the astronomical stuff. Because the theory that makes most sense in sort of the basic normal cases doesn't get it right in all cases. And what we want ultimately is a theory that gets things right in all cases. Physicists want a unified theory of everything. They want a physical theory that tells us how everything moves, down from the smallest particles to the biggest stars. And linguists want a theory of reference, so they want to know how words like names refer to things. The name Albert Einstein picks out a specific person in history. How does it do that? Why does the word do that? How does that word attach to one person? Linguists don't want a theory that works sometimes, but not all the time. They want a theory of all terms, of all reference. And similarly, in philosophy, we want theories that get things right for all cases. When we ask, what makes something morally right or morally wrong? What is morally right and wrong? We don't want an answer that just tells us the correct answer sometimes. We want an answer that's right all the time. We want a theory of what it means for something to be morally right or morally wrong. And so a thought experiment can tell us whether or not we have that sort of theory, because it can take us and let us look at the extreme cases where the theory is most likely to get it wrong, because the extreme cases are sort of the hardest to get right. And so thought experiments, we can look at the extreme cases and we can find out, does the theory get it right in the extreme cases, or does it get it wrong? Because if it gets it wrong, that means the theory is only right sometimes. And what we want is a theory that's right all the time. That way, if we get the right theory that's right all the time, we can just look to the theory and we'll never be wrong again. At least that's what we hope. So thought experiments are usually designed to test some theory. And as a result, they usually involve extreme cases. So it doesn't always need to be physically possible. So we'll look at some thought experiments that aren't physically possible. And we'll look at some thought experiments that aren't really logistically possible, meaning we couldn't pull it off even if we tried, even if it doesn't necessarily violate like gravity or the speed of light or anything. And we'll look at some thought experiments that aren't physically possible, and aren't maybe possible in other senses, but they are coherent. They are logically possible. They are conceptually possible. So there's a quick aside here I want to take us down about different kinds of possible, different meanings of the word possible. And this will come up later in the course when we talk about whether or not God exists, the issue of God being omnipotent. That if God exists, at least on many religious views, if God exists, God is omnipotent, meaning God has the power to do anything. God can do anything. Or God can do anything possible. But in what sense do we mean possible there? When we say God can do anything, does that mean God can make 2 + 2 = 5? Or make 2 + 2 = fish? Maybe not. Maybe even omnipotence shouldn't grant you that, because that's just incoherent. That's logically impossible. So there are different kinds of possible, and these will come up later in the course, which is why we're looking at them now as early as we can. So one sense of possible is physically possible. Something is physically possible if it's consistent with the laws of physics, sort of the laws of nature. So gravity, speed of light being what it is. I haven't memorized the speed of light, but it's a lot. Or the mass of an electron, or the strength of the electromagnetic force, that kind of stuff. Those are the laws of physics. So something is physically possible if it is consistent with the laws of physics. If the laws of physics don't rule it out. So for example, me flying around like Superman is physically impossible. I could not do that because gravity prevents it. The law of physics, which is the law of gravity, the strength of gravity and how it works, makes it impossible, physically impossible, for me to fly around like Superman. Now, another sense of possible, besides physically possible, is epistemically possible. And epistemic is a very fancy jargon word that no one uses in real life outside of academia, outside of philosophy and a couple other academic fields. But it basically means knowledge. If you see the word epistemic, it comes from the Greek word episteme or something to that effect. I'm probably mispronouncing it because it's ancient Greek, and ancient Greek is pronounced anciently. I'm not sure how to pronounce episteme, but something to that effect. But it means knowledge. So if you see the word epistemic or epistemically or epistemology, that's a fancy word. Epistemological, another fancy word that's going to come up in the course. Just mentally replace that with having to do with knowledge or stuff about knowledge. So epistemically possible means possible given what we know. So we all know, for example, that 2 + 2 = 4, that Baruch campus is located in New York City. We know that there was once a president of the United States named Abraham Lincoln. We know that the earth is round. We know that the sun is a star. We know lots of stuff. And so it's epistemically impossible for any of that to be false because we know it's true. It's epistemically impossible for the earth to be a flat triangle or just a straight line or a flat circle. I mean, if any of you are flat earthers, that's not my concern. But the earth is not flat. So if you're a flat earther, just mentally replace this with a different example. So we know the earth is round or vaguely round. We know it's a three-dimensional, vaguely spherical object. So it's epistemically impossible that it's flat. But it might be physically possible that it's flat. It might be physically possible for the earth to be flat. Maybe that doesn't violate the laws of gravity or anything. As long as the earth spun fast enough, maybe it could flatten out. I don't know. I'm not a physicist. But for example, it's epistemically impossible that I am not the instructor for this course. We all know that I am the instructor for this course. We've been on CUNY First. We've had our little introductory Zoom meeting. You've seen the syllabus. You've gotten emails from me. We all know that I am the instructor for this course. So it's not epistemically possible that someone else is teaching this course. You know for a fact that I'm the one teaching this course and no one else is. But it's physically possible for someone else to teach this course. It's physically possible that I don't teach this course. There have been many semesters where I didn't teach this course. And it's physically possible. It doesn't violate gravity or the speed of light or anything for a different instructor to be assigned to this course. So someone other than me teaching this course is physically possible, even though it's epistemically impossible. We know it's false, so it's not epistemically possible, but it's consistent with the laws of physics. So it's physically possible. And this can go in the other direction. So there are lots of unanswered questions in physics. We don't have a unified theory of everything yet. So that means we don't know all of the laws of physics. And there are different possible options, and we don't know which one is right. So there are some things that are epistemically possible, but they can't all be physically possible because one theory of the laws of physics is right, has to be right, and one has to be wrong. We don't know which one is right and which one is wrong, but one of them is right and one of them is wrong, which means one of them is physically possible because it is the right law of physics, and one of them is physically impossible because it's not the right law of physics. We just haven't found out that it's wrong yet, but it is wrong. So one's physically possible and one is physically impossible. But since we don't know which is which, right now, they're both epistemically possible. So even though one is physically impossible, we don't know that yet because we don't know all the laws of physics. So it's epistemically possible, even though it's physically impossible. So these can come apart. Epistemically possible and physically possible are very different. But they're not the only notions of possible. There's also logical possibility, basically meaning consistent with the laws of logic and math. So, for example, 2 plus 2 equals 4. That's a law of math. The law that if someone is over 6 feet tall, then they are over 5 feet tall. That's just really a fact about how the numbers 5 and 6 work. So that's a logical law or a mathematical law. So it is logically impossible for someone to be over 6 feet tall and under 5 feet tall, right? A number can't be greater than 6 and less than 5. Whatever your height is, it can't be both more than 6 feet and less than 5 feet. So being over 6 feet tall and under 5 feet tall is logically impossible. It's also physically impossible, but it's logically impossible. It's more than just physically impossible. No matter what the law of gravity worked like, no matter how light and electromagnetism worked, you still couldn't be over 6 feet tall and under 5 feet tall. Math is sort of stricter than the laws of physics. Numbers are what they are. 2 plus 2 equals 4 is logically necessary. 2 plus 2 being equal to 5 is logically impossible. And so if something is logically impossible, well, the laws of physics obey logic and math. So it's also physically impossible. So if something's physically possible, it must be logically possible. And if something's logically impossible, then it's also physically impossible because physics obeys logic and math, but math and logic don't necessarily have to obey physics. I mean, numbers don't have mass or electric charge or anything. Numbers are independent of physics. Numbers have nothing to do with physics except for the fact that physical laws have to obey math. They have to be mathematically coherent. So logically possible is sort of the broadest notion of possibility. As long as something's consistent with the laws of logic and math, then it's logically possible. So it's logically possible to be 10 feet tall, even though, as a matter of fact, if you could not survive being 10 feet tall, the blood from your brain would not make it to the rest of your body. Biologically, we couldn't pull that off. We couldn't be 100 feet tall. Your mass would increase at a faster rate than your muscles did. So you couldn't move around. Your heart couldn't get your blood everywhere. If you were no one could live to be 100 feet tall. No one could grow to 100 feet tall. That's physically impossible. But it's logically possible. That doesn't violate math to say someone's 100 feet tall. So logical possibility is broader than physical possibility. More things are logically possible than they are physically possible, because everything physically possible is logically possible, but not everything logically possible is physically possible. Right. And so I already talked about this. It's not logically possible to be both taller than 6 feet and shorter than 5 feet. So that's an example of a logical impossibility. And so thought experiments really just have to be logically possible. They don't have to be physically possible. we don't have to be able to pull them off. They just have to be logically possible. They have to be coherent. You can't have a thought experiment where someone, for example, is 10 feet tall and also 2 feet tall. Either they're 10 feet tall or they're 2 feet tall. They can't be both. So you can have a thought experiment where someone is 10 feet tall, but you can't have a thought experiment where someone's both 10 feet tall and not 10 feet tall. They have to be one or the other. And that'll get, I know that's a lot. That's a little tricky right now. It's very sort of nuanced distinctions, but it'll get easier as we go through the course and use that a bit more in practice, looking at thought experiments and looking at theories and arguments. So a thought experiment doesn't have to be realistic. It doesn't have to be physically possible. It doesn't have to be epistemically possible. We can know that it will never happen. But it does have to be logically possible. So it has to be logically coherent. It has to make sense. You can't say something both is and isn't true. You can't say someone's both taller than 6 feet and less than 5 feet. You can't say that something is both square and a circle. So you can say talking squirrels are fine. We can have a thought experiment where squirrels talk. And then we can ask, if squirrels talked, would it be okay? Would it be okay to kill them? Would it be okay to eat them? If pigs could talk, would it be okay to eat pork? If a computer could can talk and interact with us the way human beings do, would we have to say that it was conscious just like we are? That's one of the thought experiments we'll talk about. So they don't have to be particularly realistic. They don't have to be anything that's going to happen anytime soon, but they just need to be logically possible. They need to be coherent. They need to make sense. So flying around, floating in the air, violating gravity is perfectly fine. Having your brain plugged into a computer that feeds you whatever experiences would make you happiest, that's a fine thought experiment. That will probably never happen. We probably couldn't pull it off and probably never will. But it's a fine thought experiment because all the technical details that get in the way, we can just sort of rule out. We can ignore them. But you can't have a thought experiment where 1 + 1 = 3. That's not coherent. It's not even clear what that would mean. If you had one apple, and you therefore had 3 apples, what would that even mean? That's not clear what it would mean. And so we shouldn't use it as a thought experiment. We can't really get a grip on that stuff. So a thought experiment, just to recap, is a hypothetical case that is used to investigate a theory. So how do we use them to investigate theories? How do we use them to test theories and to look at our concepts? Well, they're usually used to test a theory, like I said, or if they're not testing a theory, they can just be used to argue against a theory, to provide a counterexample. Because even if the counterexample isn't going to happen in real life, the fact that a theory gets the counterexample wrong says something bad about the theory. It says the theory doesn't get it right in all cases. It's not necessarily true. It's not logically necessarily true. So if a theory says something false in a hypothetical case, that means something is wrong with the theory. So, for example, Schrodinger's cat. And this is a comic that I think just sums up Schrodinger's cat and what it's for pretty nicely. It's a little dismissive of normal people like us, the folk outside of physics, but that's okay. We can take it. We're thick-skinned. So, comic says what Schrodinger's cat means is, suppose that inside a box you have a cat and a glass container of poison. Suppose there is also a radiation emitter and a Geiger counter, and that if the counter detects radiation, it causes a hammer to break the glass. meaning the poison will be released and the cat will die. According to the Copenhagen interpretation of quantum mechanics, the cat is both alive and dead until something collapses the wave function. Don't worry about what the wave function or what collapsing the wave function is, but just according to the Copenhagen interpretation, Niels Bohr, etc., of quantum mechanics, if you measure quantum stuff like radiation and particle spin, then they have definite states. They are either radiating or not radiating. They are either spin left or spin right. They are in a certain location. But the Copenhagen interpretation says until you do that measurement, it's all of the possibilities at once. It's all of them at once. It hasn't settled on one way to be, one state. So if the Copenhagen interpretation is right, then the cat is both alive and dead until something collapses the wave function, namely us opening the box and checking. This is, of course, absurd. So the interpretation must be wrong. And then what people think it means, most of us probably, so there's a cat in a box and hey, maybe it's dead, but who knows? Science. And that's not what it means. What it means is this thing in the first panel here, where it's used to argue that the Copenhagen interpretation is wrong because it has this absurd consequence. It says if we put a cat and a vial of poison and a Geiger counter in a box, the cat would be alive and dead until we checked. And that illustrates very vividly that the Copenhagen interpretation is absurd. It says that the world isn't a certain way until we look at it. And that's nonsense. The world exists independent of us and our minds. We don't cause the world to be a certain way just by checking. The world is a certain way. That's what Schrodinger thinks. That's what Schrodinger was trying to say. So the Copenhagen interpretation is wrong. So the thought experiment is meant here to illustrate that a specific theory, a physical theory of what's happening behind the mathematics of quantum mechanics is absurd and therefore should be rejected. And that's a common use of thought experiments. They're commonly used to show that theories that might seem right when you look at the basic cases have absurd and obviously false consequences in some sort of more far out cases. And if the theory has absurd consequences, then the theory is absurd and we should reject it. And that's what thought experiments are used for a lot. They can also just be used to raise issues, raise questions about our concepts like right and wrong, good and bad, physical, what it means for something to be physical, what a mind is, what we as people are, what a person is. If you take a thought experiment we'll look at later in the course is if you take your brain out of your body and put it into a new body, where are you? You, the person, where are you? Are you in the new body with your old brain? Or are you your old body now without a brain? Do you go with your body or do you go with your brain? That's a question that the thought experiment where your brain is taken out is supposed to raise. What's essential to you? What makes you who you are? Is it your body? Is it your mind? Is it your brain? Is your brain your mind? Those are all questions that we'll investigate later in the course using thought experiments. So thought experiments can be used just to raise questions about our concepts, like right and wrong, about free will. Do we have free will, or are we just very complicated systems of particles just moving along according to the laws of physics with no actual free will? That's an interesting question. And thought experiments can help sort of investigate that question. What is a mind? Thought experiments can help with that question too. And we'll look at all this later in the course. So by considering weird or extreme cases, we can find out where the borders of our concepts are. And so that can tell us about what it means to be morally good, to have a mind, to survive. If you upload your memories into a computer, have you survived? Or have you made a machine that acts like you but isn't you? Thought experiments can help us try to get a grip on these questions and to answer these kinds of questions. And that's what thought experiments are also used for. They can be used just to create counterexamples to say, hey, this theory is wrong. But they can also be used to investigate concepts and to ask questions and help us get a grip on what the issues are. And that's what we're going to try to look at with thought experiments later. So one example of the sort of just investigating concepts thought experiment is Einstein's train. Einstein came up with a thought experiment where a train is moving at 3/5 the speed of light, which is logically possible, but is in fact physically impossible because the train is too massive. And we couldn't do it even if it were physically possible. We do not have the capacity to make that happen. The amount of energy it would take is enormous. We couldn't do it. So it will never happen. But Einstein's example, Einstein's thought experiment of a train moving at 3/5 the speed of light away from one bolt of lightning and towards the other, helps illustrate, helps tell us and get a grip on why in the theory of general relativity, time is relative. Whether or not two events happen simultaneously, whether or not they happen at the same time, depends on how you are moving relative to them, to the two events. It depends on your frame of reference because light isn't instantaneous. And so we don't need to worry about the physics here. I'm not going to go into that. I don't fully understand it anyway, but it's not worth our time. The important thing to take away here is that even in physics, which seems like the perfect example of real experiments with machines, testing things in the world, you still need thought experiments sometimes because they help you get a grip on the concepts involved to understand what's going on in the world. Because your thoughts are not limited by the technology available to you or what you can physically pull off. It's just logically working through the concepts involved, understanding the ideas at play here. That's what thought experiments are really for. And so that's what we're going to use them for in this course. And so now I'm going to end this video so that you don't have a super long video that you have to wait to upload, or that wait for me to upload, or that you have to wait to load on, I don't know what your internet system is. So I'm going to stop this here, and we're going to start a new video where we go through the thought experiments from the Pig That Wants to Be Eaten book together. All right, so I will see you in the next video.